Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our second set of notes from our chapter sequence, or series of chapters 17 and chapter 18, where today we'll be looking at reaction rates. Now, reaction rates really revolves around a concept known as collision theory, like kinetic molecular theory is how we explain the movements of solids, liquids, and gases and how that affects their behavior. Well, collision theory, we're looking at reaction rates and how the movements of the particles actually create the collisions that happen that lead to reactions. So collision theory is based upon the fact that reactions are caused when either atoms, ions, or molecules, just depends on what the reacting species is, collide with enough kinetic energy and the proper orientation to cause a reaction. So think of it as three key things. One, they have to collide. If they're not in the same space at the same time, they're not going to interact. They can't chemically react. Two, kinetic energy. They need enough ambient energy within the particles themselves when they collide to break apart the old bonds. And then they also need the proper orientation because certain parts of certain molecules are really involved in the reaction and other parts aren't. So it really does make a difference what the orientation is at collision. So there's three key parts here. So first, collision, I think most people get that. But the second part, the idea of orientation is sometimes a little bit more confusing. So think of a collision as like a couple of puzzle pieces. They only fit together or react in a very specific orientation. So we can try and put A and B together many different ways, but there's really one way in which they will fit together to cause a reaction. That's orientation. And orientation is particularly important when we're looking at a large molecule. So let's say we have a large hydrocarbon, a string of a whole bunch of carbons in a row. And really what's happening is, let's say there is a specific part of this molecule that's actually reacting with something else. Well, no matter where you collide on this molecule, if you're not interacting with the OH, if that's the active thing, then that's not going to lead to a proper orientation to cause a collision. The collision needs to happen down here to interact with that OH. So, case in point, if you look at the reaction between HCl and C2H4, there's a very specific part of the HCl molecule and a very specific part of the C2H4 molecule that are involved in the reaction. And you can see here the hydrogen, which is the small white area of the HCl. So here is the hydrogen, is actually interacting at this double bond site. So in this particular case, when that hydrogen collides in that area, so that the hydrogen part of HCl is colliding with that double bond part between the two carbons, you get a successful potential collision here. But in every other instance where the non-hydrogen, or it's the hydrogen but it interacts at a different spot than the bonds, all of those leads to non-successful collisions. So only collision one is a proper orientation to actually lead to a reaction. Now the next thing would be, does it have enough energy? Because it's just going to bounce off if there isn't enough energy to break apart the old bonds to reform new bonds. Now, how much energy that takes is that activation energy. So it's the minimum energy needed for a successful collision. So think of it as this person rolling this ball up the hill. Now, if he pushes it hard enough, it'll roll up that other hill, crest the top, and then roll down to the far side. But if he doesn't push it hard enough, it's just going to roll back to the initial position. Now, if it reaches the top of that hill right here, in an actual chemical reaction, here we've got reactants, here we've got products. So what do we have at the top of the hill in between the two? Well, that's what we call the activated complex. It's a temporary unstable arrangement of the atoms that may form products or actually may go back to the original reactants. But if we've got enough energy, it's going to end up making our products. So up here, we have kind of a combination of the two reactants coming together. So for this brief instant in time, we have all of these things combined in this very unstable temporary complex known as the activated complex. It's sometimes referred to as a transition state because it's in between reactants and products. Now, when you look at this particular energy diagram, one of the things that you should be able to identify from energy diagram is whether the reaction is endothermic or exothermic. So take a look at the actual reactant themselves. And remember, we can ignore the hill. All we really need to key in on is where do we start and where do we end if we're talking about whether the reaction enthalpy change is endothermic or exothermic. Well, if we're starting at reactants and that's higher in energy and we're going down to products, that meant the reactants must have lost energy. Energy that leaves the system, lost energy, would be exothermic. So this would be an example of an exothermic reaction. Now, one of the things I want you to be able to do with a reaction like this on the test is be able to identify the key parts of the energy diagram. So the first thing you should know is where we start, far left in the reaction process, that would be our reactants. Far right, we've got our products. And remember, at the top of that energy hill, at position C, we have the activated complex. And the height of that hill, which is represented by D here, from the reactants to the top of that hill, that would be our activation energy. So energy of activation, the minimum amount of energy needed for a proper orientation to give us a successful collision. So what does that leave? Well, we just talked about region E. The difference between reactants and products is our enthalpy change. So from last chapter, that's our delta H. And in this particular case, because products are below reactants, that means we lost energy. It's a negative delta H, and that would represent an exothermic reaction. So what would an endothermic reaction looks like? Well, it's the same kind of thing. We have reactants going up a hill to the activated complex and then come down to our products. We still have an energy of activation. The forward side of that hill from the reactants up to the top is our energy of activation. But in this particular case, our products are above our reactant energy. So that would be an endothermic reaction. So your products above reactants, that would be recognized or representing an endothermic reaction. Now, reaction rates are the speed with which a reaction occurs. And you need to understand not only what causes a reaction, the whole collision theory, but what can we do to speed up or slow down reactions? And how do we actually measure it? What really is a speed? Well, the speed of a reaction is known as a reaction rate. All rates are a change in something over change in time. In the case of your automobile, it's a change in distance over a change in time. In case of a chemical reaction, the average rate of reaction would be the change in concentration of one of the species over a given amount of time. So change in concentration over change in time. Now, rates are always expressed in positive values. So remember, if you go to do and calculate a reaction rate, remember you should always get a positive value. And the reason I mention this is because when we have reactants becoming products, our change in concentration, the number on top here, is actually going to be a negative value because as reactants get consumed, our final value is less than our initial value. And when you take a small number and subtract a big number, you're going to get a negative. So how do we handle that and make it positive? Well, we just multiply by -1. So because we're usually measuring by how fast reactants are consumed, you're often going to have to do this. So in the case of a reactant, so if you ignore what's over here for a second, in the case of a reactant, it would be the change in concentration of our reactants over the change in time multiplied by -1. So in new reactants, they're going to be going down in concentration. We're going to get a negative value. So to make it positive, we have to multiply by -1. But when we're looking at it from a product point of view, which we sometimes do, not as often as reactants, but sometimes we'll look at it from the product point of view, we're going to get a positive value. So we don't have to multiply by -1 over here. Now, the brackets mean something very specific, and it's something you should be familiar with from our last test. Brackets represent concentration in moles per liter. So really, anytime you see brackets in an equation here, that means molar concentration. So we have to be dealing with moles per liter or molarity when we're calculating our changes in concentration. Now, one of the things you may end up seeing it sometime or another in this chapter is this kind of graph. It's what's happening to concentrations of reactants. Notice it says reagents. That's just another name for reactants. And products versus time. Well, if we're flat, that means our concentration is not changing. But if we are a steep line, whether it's up or whether it's down, if we're a steep line, that means our concentration is changing very rapidly. So that must mean at the very beginning, it looks like a reaction starts very fast and then slows down. Well, why would that happen? Well, it's actually tied to collision theory. And it's something that I think conceptually you can understand here. At the very beginning, we have all kinds of reactants because they haven't reacted yet, and very little products. So that means if we have a lot of reactants, we've got a lot of reactants colliding. And remember, collisions cause reactions when they're proper orientation with enough energy. So the more collisions we've got, the greater the likelihood we're going to get a successful collision. So when we got a lot of reactants, we should have a very fast rate. And then as time goes by, that rate should be slowing down from a reactant point of view. So what you're seeing here in this graph, steep at the beginning for both reactants and products, would make sense. Now, calculate the average rate of reaction expressed in moles of H2 consumed per liter per second. Well, that just means molarity because that's moles per liter. And then per unit time, that would be in this case, they're asking us to calculate it in per second. Well, in order to do this, we need some data. So let's say we have this reaction between hydrogen and chlorine gas to make HCl, hydrogen chloride. So here's our balanced equation. At time 0, this would be the initial concentration of H2 and Cl2. And notice we have 0 HCl at the beginning because the reaction hasn't started yet. But after 4 seconds of time, my H2 has dropped to 0.02, my Cl2 has dropped to 0.04, and my HCl has risen to 0.02. So you can see that as time is progressing, our reactants are being consumed and our products are being formed. Now, the average rate of reaction with respect to hydrogen, because we can't just use all of our numbers here. We have to look at it from a specific point of view of a specific species in the reaction. In this case, we're looking at it from hydrogen because it says calculate the average reaction rate expressed in moles of hydrogen consumed per liter per second. So we need to take the final concentration of hydrogen minus the initial concentration all over T final minus T initial, and then I have to take that entire quantity and multiply it by -1. So if I actually plug in the numbers from up above, notice 0.02 minus 0.03, that's going to give us a negative value. That's why we multiply by the -1 in front. And then on the bottom, we're going to have 4 minus 0, which is just going to be 4. So when we actually calculate this and plug the numbers in our calculator, we end up getting a positive 0.0020 molarity per second. And yes, we could also write it over moles per liter seconds. That would be the same thing, but it's just easy to write it as molarity per second. So this would be the average rate. And notice it is a positive value. Now, that's what it would be if I calculate it with respect to hydrogen. Now, what would it be if I calculate it with respect to chlorine? Well, my chlorine numbers are here. The time is going to be the exact same, so that's not going to change. Notice 0.04 minus 0.05, it's still going to give us negative 0.01. So it would have the exact same reaction rate with respect to chlorine, which makes sense. I mean, on the surface, if you think about it, this is the same reaction, so my reaction rate should be the same. Well, let's take it one step further. Let's look at the reaction rate with respect to HCl. Now, while our time interval is the same, now we're looking at this. And now we don't need to multiply it by -1 because when we do final minus initial, we're going to get a positive value. We're dealing with products here. So we take 0.02 minus 0.01, which on top is going to give me twice 0.01, and now it's going to be 0.02. And on top, or on the bottom, it's still going to be the same old 4 seconds. So this looks like it's twice as big. Well, why would it, with respect to HCl, be 0.0050 molarity per second? It's the same reaction. Why would it be faster? Well, pause and think a second here. Go back to our balanced chemical equation. 1, 1, 2 are the coefficients. So that means I'm using up hydrogen at the same rate as I'm using up chlorine. Those should be the same calculated average rate. But I'm making my HCl twice as fast as I'm consuming my H2 and Cl2. So with respect to HCl, it should be twice the number. And that's exactly how it calculated it out here. Now, what factors, so we're going to go a little bit deeper in collision theory, what are things that can affect the rate of a reaction? Well, one of the major ones is temperature. Now, don't confuse this with what we talked about with dissolving. So we talked about, what can make things dissolve faster and what can make things dissolve more. Here we're looking specifically at how changing temperature affects the actual rate of a reaction, the speed with which the reaction occurs. Well, first off, if we increase the temperature, that usually increases the reaction rate, and it does it by a significant amount. Why? Well, think about it. If you increase the temperature, that means the average kinetic energy of the particles is increasing. That means on average the particles are moving faster. Well, if the particles are moving faster around a container, they're going to bump into each other more often. More collisions, higher rate by collision theory. Now, there's a twofold effect here because when we increase the temperature, not only are we increasing the speed with which the molecules move, we also increase the energy of the resulting collisions. We're going to have more high energy collisions. So not only do we get more collisions, and let's say 20% of our collisions are successful, 20% of a larger number is going to give us a larger number, more successful collisions. But if we increase the energy of those collisions, that's going to give us even a higher percent that will be effective. So it's not just 20% of a larger number is larger, but we're increasing that 20% as well. and then taking of a larger number. So fundamentally, increasing the temperature rapidly changes the reaction rate. A rule of thumb is typically that for every 10 degrees, you see your reaction rate doubling, which means when you go from 10 to um, 20 degrees Celsius, typically you'll see a reaction rate double. Go from 20 to 30 and you will see it double again. So for every 10 degrees, you typically see a doubling of reaction rate. Now, one of the diagrams we looked at before um, was this diagram dealing with the average kinetic energy, or I should say the kinetic energies of a certain percentage of molecules. So if you look, the high point of the hill is right in here. So for the red one, our average kinetic energy is over here. And for our blue one, our average kinetic energy is probably going to be somewhere over here. So what we talked about this diagram last time we looked at it was, well, you can see when we increase the temperature, we're increasing the average kinetic energy. So the height of the hill is smaller in the red situation, but it's significantly greater in average kinetic energy. And that was what we used the last time we talked about this diagram. Well, let's impose on this what happens if the energy of activation is that kinetic energy right there. So let's say that's our magic kinetic energy. You can see in the case of the cold substance, we do have particles with enough energy to cause a successful collision. But look at the difference between the cold and the hot. In the hot situation, we had a significantly, oops, shaded in too many of those there. We have a significantly greater percentage of particles that have enough kinetic energy to have a successful collision when it was hot. So you can clearly see changing the temperature does a lot to change your rate. Now the second thing is concentration. Concentration is probably even more important than temperature because we're going to end up using this a lot in the last equilibrium section in chapter 18. So we're going to come back quite a bit to concentration. Now concentration is the amount of particles per given volume. So if we increase the concentration, that's going to increase the rate. Why? Well, if we've got a whole bunch more particles, we've got a whole bunch more collisions. And when we increase our number of collisions, we're going to increase the number of successful collisions. Third one here is particle size. Now, particle size on the surface sometimes confuses people, but if you think about it as effective collisions, when we have smaller particles, because we've taken a large chunk and we've broken it up into little pieces, we've dramatically increased the surface area. And that's going to lead to a faster reaction rate. Why? Well, once again, it's about our collisions. We're going to get a lot more collisions. But it helps to see this at a particle level is to understand why breaking it up is going to cause that to happen. So if we have one large chunk, the only place that it can react is on its outer surface here. So all of these in-between areas that you see as dotted lines, the reactant particles can't come together inside there because they can't get in there. So the only place they can react is on the outer surface. When you take a large object and break it up into smaller pieces, you dramatically increase the surface area. And now reacting particles, the little red circles that you see, can get to all of those places that they couldn't get to before at the very beginning. So with this large cube, we would have to wait until it reacted away its outer layer to get into some of those inner areas to react. Here, they're all accessible where that dotted line was. So that's going to give us a significantly greater number of collisions. So if we want to increase a reaction rate, we just break it up into little pieces. Now, last one we're going to look at here is a catalyst. Now, catalyst is one you should already know the answer for because we talked about this in an earlier chapter. Adding a catalyst increases the reaction rate. The one thing we never really talked about was why, because our definition of catalyst was a substance that increased the speed of a reaction without being consumed. So it looks like on the surface it's not doing anything, but without it there, the reaction doesn't happen near as fast. So it must be doing something at the particle level. Well, it won't be until next set of notes that we really get into on a particle level what a catalyst is truly doing. So at this point, we're just going to describe the fact that it increases the reaction rate, and we are going to scratch the surface. We're going to say that what actually happens when you add a catalyst is it lowers the energy of activation. Now, how is something we're going to get into when we get into reaction mechanisms. But here, what I want you to understand is the blue situation is our uncatalyzed reaction. So we've got a relatively large energy of activation. And remember, the larger this energy hill is, the more energy our reactant particles need for a successful collision. That means a slow reaction. So the bigger the hill, the slower the reaction is going to be by collision theory. But when we add a catalyst, what it actually does is it gives us a low energy pathway. The red is our catalyzed reaction. So before, all of these collisions in this range were unsuccessful. But with that catalyst mix in there, they now become successful. So it lowers the energy of activation in essence. It gives us a low energy pathway for the reaction to occur, and therefore collisions that weren't successful before because they were too low in energy can now be successful. So it dramatically speeds up the rate of a reaction. So catalysts are hugely important in industry, especially because they're not consumed. Why aren't they consumed, and what are they really doing? We'll see in the next set of notes. Now, the last thing I want to talk about here is an inhibitor. Not because this is a big idea in the chapter, but because it's a common misconception. People know there are some chemicals which speed up reactions, and there are other chemicals which can slow down reactions. They would be called inhibitors. Now, on the surface, it would make sense, or at least seem to, that if a catalyst lowers the energy of activation, then an inhibitor must raise the energy of activation. And that's completely false. While it does decrease the reaction rate, it doesn't actually change the energy of activation. What catalysts typically do is they slow the reaction by literally lowering concentration. They react with one of the reactants. Maybe they are reacting with a catalyst, or maybe they're reacting with an intermediate, something we'll talk more about next. Intermediates are things that don't appear at the beginning and the end, only exist in the middle of a reaction. But they're there and they're reacting, so if they're gone, that would slow down the rate. So this ends up then slowing down or preventing the reaction from occurring. So it doesn't change the energy of activation. It's just actually removing key components. And that lower concentration means lower collision rate. Now there is a movie about collision theory that you can watch related to this that reviews overall what we just talked about. And that ends our discussion on reaction rates.